Hi everyone, I'm Liao Zhiqiang. Welcome to the course Data Science for Business 2. This is the first online lecture that I've ever given, and I'm very excited to tell you about it. Here you can find my email. If you have any question after this lecture, please don't hesitate to contact me. Today, we're going to talk about the introduction to convex regression. I'll tell you what is convex regression, what the models are good for, and how we can use them. Before we go to the convex regression, I would like to give you a reminder about the general regression problems. I guess you guys have different backgrounds, but regression problems are very common in many areas. For example, in statistics, economics, and machine learning, etc. In this lecture, we're talking about the regression problems in a framework of data science and machine learning. Many machine learning tasks can be seen as learning a regression function. The process is, at first, we need some data, and second, we need a regression model. For example, the linear regression model. Then we can learn a function from the data by using the regression model. Last but not least, we can use the learned function to predict future things. Here are some examples. We can predict the price of a stock in 6 months from now on the basis of companies' performance measures and the economic data. We can predict the amount of the glucose in the blood of a diabetic person from the infrared absorption spectrum of that person's blood. And we can predict the controllable cost of the Finnish electricity distribution companies based on the statistical data. A good regression model is that one that accurately predicts such outcome. In regression problems, we first need some data, including inputs x and outputs I. The regression model is yi equals fxi plus epsilon I. The regression problem is to learn a function fx that can predict y from x. Here is an example. We can predict the housing price in Boston metropolitan area. I plot the dataset from the Boston housing dataset in the graph. I use a linear regression to figure a linear function. As you can see in the graph, the linear function describes the relation between the distance and the housing price, also the age and the housing price. But what are the problems with the linear regression? Well, linear regression makes a very strong assumption on the shape of the estimated function, which must be linear. In the example, we want to predict the housing price in the area of Boston. But the relation between housing price and the distance is not linear. As you can see on the graphs, the distributions of the data points seems nonlinear. Such relations in many real problems are convex or concave. This motivates us to use the convex regression. So, what is convex regression? Basically, convex regression is also a regression problem, but we aim to fit a convex function through the convex regression model. The process is, at first, we also need some data, and we need a convex regression model. Then we can learn a convex function from the data by using the convex regression model. In this picture, I plotted some data from the Boston housing dataset, and we can fit a concave function, which is black line, in the right figure by using the convex regression Python package. I'll tell you more about this Python package in a bit later slides. Here I would like to give you some basic facts about convex regression, including the notations and the model. In the previous example, we use the MEDV, or the median value of the housing price, as the response variable or targets that we wish to predict. We generally refer to this response variable as y, and we use the distance or DIS as our explanatory variable, or feature, or regressor, you can call it as you wish. And we name it as x1. If d features are included, we can refer to this feature as our vector x, which includes d elements. Now we write our convex regression model as follows. This formula is very similar to our general regression model. The only difference is that the f function is a concave or convex function. So here the n is the sample size or the data size, and the d is the dimension of the x variable. Epsilon captures the measurement errors, and we'll also call it error terms, if you are familiar with regression problems. In the next video, I will tell you how to estimate the convex function fx, and I'll see you in the next video. Hi, welcome back from the break. So, how to estimate the convex function fx exactly? In this lecture, I'll tell you how to use the least square estimator, which means that we just consider the squared loss function as follows. Of course, there are some alternative loss functions that you can use. For example, absolute loss, quantile loss, or Hilbert loss. The least square estimator for convex regression is defined as follows. On the left-hand side, the fn height is the estimated function. On the right-hand side, this is a function to minimize the sum of square errors. And the class f calligraph contains all convex functions. Here I give you a very intuitive example to illustrate the least square estimator. On the graph, I plot the data from the Boston housing dataset, and also a potential concave function. The dashed line represents the distance between data points and this function. So, the least square estimator minimizes the sum of squared distance between the data points and the estimated concave function. We also call it residuals. After we have this least square estimator, so how we can calculate the parameters in the function? We can use the optimization problem. The convex regression problem can be rewritten as the following finite dimensional quadratic programming, or QP problem. In this optimization problem, the objective function is to minimize the sum of the squared residuals, or the sum of epsilon I squared. In the constraint, the first constraint called the regression function. We use the similar regression function in linear regression. Here we have the second constraint. The second constraint is the shape constraint, which imposes concavity. If we remove this constraint, this QP problem refers to the ordinary least square, or OLS regression. In the shape constraint, if we use greater than or equal to, the estimated function becomes convex. If we use less than or equal to, then the function is concave. This QP problem can be solved by many off-the-shelf interior points solvers. For example, Groby, Mossack, and Seplex. After calculate the parameter from the optimization problem, so what is the learned function exactly? Here I give you an example about this learned function. On the graph, the learned concave function is the bold solid line. As you can see on the graph, we actually estimate multiple linear functions to approximate the concave function. The estimated concave function is the lower bound of all linear functions. The formal expression of this learned function is fn height of x equals the minimum of alpha I hat plus beta I hat times x. Here the minimum means the lower bound. If you want to estimate a convex function, you just need to change the minimum to maximum. Here I give you an illustration about this shape constraints. As we discussed in previous slides, the only difference between convex regression and a linear regression, is that we use the shape constraint. So, how shape constraint make the estimated function become concave or convex? In this picture, we can write the shape constraints on data points x1, where I equals 1, h equals 0, 2, and 3 on the red dashed line. We write this the constraints as follows: 3 constraints. What those constraints mean? Well, as you can see on the graph, the value on the estimated function is the lowest one among others, which means that the lowest red point is the smallest value among others data points or red dots on others linear functions. Here I have a question for you. In the optimization problems, how many shape constraints do we have in total if we have n data points? I'll give you 1 minute and you can think about it. Now, I guess you have your own answer in your mind. How many shape constraints in total in the optimization problem if we have n data points? Well, the answer is we have n squared shape constraints, or n times n shape constraints in total. In the next video, I'll tell you how to use the convex regression in the real world. And I'll see you in the next video. Hi, welcome back from the break. Now, let's talk about how to use convex regression in the real world. I'm very excited to tell you that now we have a Python package for convex regression. It's very convenient to use it, and I'll show you in a few slides. On this picture, this is the GitHub homepage for this package. If you want to know this Python package by yourself, please click the link down below. The installation is very simple. you can use a pipe to install this package on your own computer or on Google Colab. I highly recommend you to use it on Google Colab because it's very simple. We currently have two models. The first is CR model or convex regression model that I would like to show you by a couple of examples. The second model is PCR or penalized convex regression. I leave this one as an exercise for you. You can compare these two methods or two models by yourself and see what's the difference between them and which models should I use in your specific application. In this package, we solve the optimization problem that I've shown you by using the solvers. For illustration purpose, the built-in solvers are enough. But for big data problem, commercial solvers need to be installed by yourself. For example, you can use Gurobi, Ciplex, or Mosaic. Then I'll show you what parameters that we have in the CR model. Well, here we have 4 parameters in the CR model. The first one is the shape. The options include convex or concave, which means the shape of the estimated function. The second parameter is positive. The default value is false. If you set this parameter as true, then the coefficients of the estimated function should be positive. The third parameter is fit intercept. The default value is true. If you set this parameter as false, then the estimated function doesn't have the intercept. The last parameter is solver. Here we have lots of options. The default value is equals, which is an open source package for solving quadratic programming problem. Here we have another 2 open source solvers that you can choose, including OSQP and SAS. If you want to solve the big data problem, you should install other commercial solvers by yourself. Here I would like to show you an example by using the generated data or the fake data. The benefits of using this data is that we have the true function. So here the true function is fx equals x squared plus 3. Then we randomly generate the data. The xi is from a uniform distribution from -1 to 1. Yi equals xi squared plus 3 plus error term. The error term epsilon is from the normal distribution with 0 mean and the sigma standard deviation. I plot 100 generated data on this graph. As you can see the blue dots. Now also plot the true function as the black curve on this graph. So the regression problem becomes estimating the function fx. If the estimated function is close to the true function fx, then we can say the model is good. Then we use the generated data and fit the convex function. I plot the estimated function on this graph as the dashed line. As you can see, the fitted convex function is very close to the true function, which means that the estimated function is good, or we can say the model is good. The fitted convex function is actually a piecewise linear function. The benefits is that the CR model can approximate more complex function than fx equals x squared plus 3. Here is another example. I show you how to use the multivariate regression in convex regression, which means that we have three variables, including x1, x2, and x3. We first need to generate the data. I show you how to write the Python code on this picture. And then we can fit the model by using the CR model. We fit the convex function, and then we learned the function, and the final step is predict y from the unsigned data points x0. x0 is 0.2, 0.3, and 0.5. The given value of the y variable is 3.22. As we can see, the true value is 3.38, and this estimated value is very close to the true value. And then we also can see that the CR model is good. I also compare this result with the results from the linear regression. The given results from the linear regression is 4.02. It's a bit far from the true value. You can try this example on Google Colab by clicking the link down below. Then I would like to give you a real-world example. Here we use the production dataset. We're supposed to predict the outcome or the total production of the firms. Here we have two inputs or features in this dataset. The first input is the neighbor, which represents the person hours worked in a year. The second one is capital. This is the measure of all machinery, equipment, and buildings. The response is output, which is the real value of all goods produced in a year. We have 60 data points in total, which is also the number of the firms. If you want to know this dataset, you can open the website and read more about it. So here the task is to fit the Cobb-Douglas production function, which is concave. The first step is to load the dataset. By using this package, it's very simple to load the dataset. You don't need to download the dataset from somewhere else. You just use one line of Python code, and you can load the dataset, as I show you in the picture. The second step is to split the datasets into 80% training set and 20% test set. Then we fit the concav function with the training data. The next step is to predict the test data. As I show you on the picture, we calculate the mean square error, or MSE, from the CR model. We actually measure the model's predict performance by using mean square error, or MSE. As may you know, the lower the MSE, the better the model. So the given results of the CR model is 64. I compare these results with that's from a linear regression model. The results is 74. It's a bit bigger than the results from the CR model. And we can conclude that the CR model performs better than the linear regression model. You can try this example on Google Colab. I gave you a link out there. At last, we have some references. Of course, you can contact me at my email and report the issues and bugs at our GitHub homepage. You can explore more demos and examples at the website of this Python package. I also give you some literature you can read if you want to do research or if you are interested. This is all of the lecture, and I thank you all for listening. Goodbye.